Another important feature of a linear transformation is called its range. And this has the same meaning that it has when dealing with functions. Given any linear transformation that sends one vector v to another vector u, the range consists of all possible output vectors u. And given this definition, there's a natural problem that arises. Suppose I have a linear transformation, how do I find the range of that transformation? So let's see if we can solve this problem. So first of all, we might want to remember that any linear transformation can be described in terms of a system of linear formulas, and the coefficients of these formulas can be turned into our transformation matrix. So any linear transformation has some corresponding transformation matrix associated with it. And remember that this transformation matrix is going to be the same as the coefficients of the system of linear equations that describe how to obtain the vector u from the vector v. Since we want to find the range of the linear transformation, let's remember the definition. It's going to consist of all possible output vectors u. Well, that seems like a really daunting task. How do I find every possible output vector? And the answer to that is, I don't know. But I can probably determine if a particular vector is in the range. And that's because if I know the components of the vector, then they're going to be the constants in a system of linear equations. And this leads to an important strategy for solving problems in linear algebra. If you want to solve a problem, set up and solve a system of linear equations. So to find the range, we'll set up an equation. So if I have a vector, it will be in the range if the system of equations is solvable, and I can answer this by row reducing the augmented coefficient matrix. Well, paper is cheap, pixels are cheaper. Let's try and solve this and see where we go. So suppose we want to find the range of our transformation. We can row reduce the augmented coefficient matrix. So the first row has pivot 2. We'll multiply the second and third rows by 2. We'll add multiples of the first row to clear out the entries below the first row pivot and get a new matrix. Moving on to the second row, the pivot is 7, so we'll multiply the third row by 7 and add a multiple of that second row to eliminate the entry below the second row pivot. Since v4 is never the leading variable, it'll be our parameter. And the thing to notice here is that whatever the values we have for u1, u2, and u3, we will be able to find a solution in terms of v1, v2, v3, and v4. So since this transformation takes vectors with 4 components to vectors with 3 components, what this means is that any vector with 3 components can be produced by transforming a vector with 4 components. So the range includes any value of those vectors with 3 components. As another example, let's try and find the range of this linear transformation. And our transformation takes vectors with 2 components to vectors with 4 components, and we can find the range by solving a system of equations. So as before, we'll reduce our augmented coefficient matrix. And this time, notice that our last 2 rows give us a system of equations. Now, at this point, we could say that our range is limited to those vectors with 4 components, u1, u2, u3, and u4, where the components satisfy this system of equations. But we won't. And the reason is that we always want to express the answer to a question in the same language that the question was asked in. In this case, because we're looking for the range, and the range is a set of vectors, we actually want to answer our question in terms of the vectors in the range, which means we want to express the solutions to this system of equations as a set of vectors. Fortunately, we already know how to do that. So we'll rewrite our equations in standard form, and then reduce the coefficient matrix. And we get our system of unknowns in row echelon form. And since u3 and u4 are never leading variables, then we're going to need to parameterize them. So we'll parameterize u3 and u4, and then substitute them back in to find u2 and u1. And this gives us a way of expressing our range as a set of vectors. And so now we can express the range of this transformation as a linear combination of two vectors.